back if they're ready to start. Oh, they must be ready because now I'm live. Okay. Okay. Good morning, good late morning. It's my pleasure to be the chairperson for the session on manufacture and industry. I'm Jeff Manber, CEO of Nanoracks. And it's also going to be quite interesting for me because I'm going to learn a lot today about life sciences, on the life sciences and space, and which is really in line with the extraordinary subject matter that we've had this day and a half now. I'm really struck by the range of topics and the range of experts, and I've been in this business a long time, and it's been very nice for me to learn about the whole range of research that's been going on. So we're going to begin now with, if I may invite to the stage a keynote, Life Support Systems in Space by Frank Prudhomme of Kinetic Space in Antwerp, Belgium. Thank you.
Okay, slides, all right. Okay, so my name is Frank Prudhomme. I'm the commercial director at Kinetic Space NV, which is a company. Oh, just have to point there. Is it the other? Mm. Yeah. That's down-to-earth technology. I'm not familiar with that, sorry.
Oh, yeah, okay. You have to switch it on there.
Okay.
I go back?
No. Yeah, so that's fine. Yeah. Okay. Yeah, so it seems to work. Okay. So, yeah, I was saying I'm a commercial director at Kinetic Space NV, which is a relatively small company based in Antwerp, Belgium. And we, despite the fact that we are relatively small, we've been active in space for now over 35 years. And we've been building all kinds of space infrastructure, both unmanned, so satellites, we've built full satellites. But we've also been quite heavily involved in manned space activities from the start, now for quite some time. And obviously that's what we're going to talk about here, because if you want to live in space, you have to understand how people actually will survive a space environment, and that can start already by looking into, by doing some research activities. Most of the people will probably be familiar with the fact that if you put humans in space, lots of things change to your human body, and it will be important to understand all of this, and therefore there has been lots of research done over the last decades, and this is still going on to a large extent on the International Space Station. And obviously you can do all kinds of research on people that you have in space, actually the astronauts, and I've seen that we have some astronauts that will be talking this afternoon and will share some of their experiences. But you can also look actually to more biological models of human beings and to study that. That could be animal models, or that could be cell cultures that you cultivate and that you grow in space and try to understand how to develop and how they interact on the not always benign environment of space, because there is radiation, there is all kinds of temperatures, environments which are different from what we have here on Earth. Now, people don't only study actually human beings in space, because if we want to talk about life support systems, they are indeed meant to support the life of human beings in space. But you have also life support systems making use of biological specimens. And if we want to use such bioregenerative life support systems in space, well, we have to understand how these specimens behave in space. And these specimens are then microbial bacteria, which can actually decompose waste material, or algae, which can produce oxygen, for instance. And you see, I don't know, this is the pointer. So you see here, for instance, in an experiment where we have been growing algae in space, and these algae produced oxygen for the crew. Obviously, you see this is a very small bioreactor, actually, so will not be sufficient to really sustain humans at this size, even not a mouse. But okay, it was more to demonstrate that these things are possible, and also to understand if you put such living creatures, which algae are, in space, they will also adapt to space. And so we've been measuring the growth curves of these algae. So how will these algae reproduce in space? So if there is a next generation of algae, will they still be as efficient in producing oxygen? Or will they maybe lose some efficiency? Will they grow faster, slower? So they will also adapt to the space environment. And if we want to use so living creatures in life support systems, we really have to understand how these creatures will adapt. Because we will have to feed this into biological models, which you can then use to engineer your life support systems. And that's, okay. I'm not sure where I have to point. Okay. So that's what we are actually doing, engineering life support systems, where you look to the architectural design, process design. You can actually, well, you will have to develop some very specific technologies which are not always present in systems on Earth and different kinds of equipment. So life support systems is about keeping humans alive in space. What do you need for that? Obviously, you need food every day. You need water. You need oxygen. And, well, human beings also need some comforts. And this is, for instance, air conditioning system, that you have, let's say, benign environment where you can, as a human being, can function practically. Now, our focus of our company has been mainly on water. And why water? Because, well, obviously water is a very important component of that. But also water is actually the basis of other elements. Okay. Is the basis of other elements. You can use water to create oxygen by hydrolysis, by electrolysis, and you can also create fuel. Yeah, from water. So water is the basis for other components, actually, and therefore, yeah. Yeah. Okay. I'm doing that, but yeah, okay. Yeah, maybe I'm not pressing hard enough, sorry. So water can be used to produce other components. Obviously, water is very important if you want to produce food, as it is here on Earth. If you wouldn't have water, you can't grow crops and so on. The same will be valid if you want to do that in space. And actually, at the moment, astronauts are using was a kind of freeze-dried food, and you put water, and then you have your food produced. You can also use it for energy maintenance because it has a large capacity to store heat and so on. So you can use it in your air conditioning system. There have also been concepts to use water as a shield against radiation on trips to Mars, also where you are exposed to heavy radiation for a considerable amount of time, and you will have to shield human beings from that. But also very, very important is that water is actually an excellent transport and process medium. And in your life support systems, you will be using, if it's a physical chemical system or a biological system, you will always be using water as a medium to transport or to process your media. And actually the characteristics of the water that is used in these larger systems will actually define the efficiency of the system. So therefore, water is a very important component. And there is another reason why we actually focused in Belgium on water, is that in Belgium, it's you see here a map of the world. So we have very limited access to renewable water resources. So therefore, there is a very strong competence in water treatment technology, and that's exactly the same type of technology that we need in space, and we can take profit of that. What is the objective of life support in low Earth orbit or in human space exploration? In low Earth orbits, well, you see that water is recycled to a certain extent. It's treated, urine is collected and reused, condensed water is collected and reused, with a claimed efficiency of 90%, but in practical, it's actually only about 75%. There are a number of reasons for that, and I will explain more about that later. There is also carbon dioxide, which is removed, and oxygen, which is generated, which is obviously necessary to keep the air in the space station as a healthy environment. And then there's obviously the air conditioning, which I think is a more trivial part of it. Now, if we want to go to human space exploration, you will have all of that, but you will have a large benefit of improving the efficiency, because if your efficiency is only 75%, it means that you still have to bring 25% of water up and down by logistic means, which might be fine to do to a space station which is only 400 kilometers away, but which is much more complicated if you want to bring it to the moon or even to Mars. And now on top of that, if you go to planetary systems, well, there will be also the need to produce food of your own, because, well, you can obviously challenge, you can bring food in freeze-dried form and so on. Well, you will have to bring a lot of food if you want to go there for a longer term. Again, a lot of miles that you have to take with you. And, well, we have to think about waste processing and recycling. Obviously, you could argue that you could use the moon or Mars as a waste dump, because at the moment no one's living there. But it's much more intelligent to use this waste and to use it for energy or even food production. And a thing which you don't have in the space station, obviously, is in situ resource utilization. Okay, there might not be a lot. It's some rocks and ice, and well, we still have to find out what else we can find on the Moon and Mars. But at least there are methods to produce oxygen or water on the lunar or Mars surface, which is more intelligent than bringing it with you, obviously. So there are new challenges to be tackled if you go beyond low Earth orbits. Now, if we first look to the low Earth orbits and the existing system on the space station, so this is what is exactly currently existing on the space station. So it's a limited system, so it's not a fully recycling system. So you have the crew here in the middle, and then here you have the part of regenerating oxygen. Well, you take some contaminants out of it by filters. You remove carbon dioxide, which you dump actually, while you could reuse it for other means. But at the moment it's dumped. And then after conditioning the air, it's used back by the astronauts. You also remove condense from the air. That's the humidity control system which does that. You have humans who produce wastes and urine. And these parts of the urine and the condense are currently used in the water recycling system on the space station, and this is mixed with the hygienic water, so which is the water which is used for washing yourself, and this is also further recycled then. And some of the water is then further used for the oxygen generation. So what we are currently have been looking at is to a more advanced scenario of that. And so apart from doing the things that they are already doing, well, we want to look to also use water actually as drinking water, which is currently not the case, which also to use this for to hydrate the food. At the moment, well, there is no real surface water because they don't really do a laundry. But if you think about future and exploration, these might be things that you, will be needing, and that will also will need water and will produce water. And then on the wastewater to be used, so not only the condense or the urine and the grey water, but there is also actually black water from the toilet flush, which you could actually reuse, which we actually do here on Earth. So why wouldn't we do it in space? And on top of that, well, there are some other technologies that are producing wastewater that could be recycled. So this is actually the amount of water that is used by crew. So it's expressed in kilogram per crew member per day. So you see it's about 14 kilograms. That is what we used to build our system. At the moment, the use on the space station is more limited, especially, I think, for the hygienic water. They're asked to use less because the system is not as efficient as it should be at the moment. So the values that we currently are assuming in our system is actually higher than the ones that are on the ISS, and obviously what is produced is more or less the same. These are kind of standard values they're using. And if you want to use water not only for hygienic reasons, but also for drinking, for instance, you see that there is a lot of more contaminants in the water that you will have to remove in order to be able to use it for the purpose that you need. So why is the current system not able to cope with that? So it has two main disadvantages which limit the recycling efficiency of the water to only 75%. And the 75% comes from a loss of efficiency by, let's say, biofilms and scaling in parts of the system which limit the performance, or which will block part of the system so that you have to do maintenance, and therefore the system is not all the time operational. So that's so you lose 2 times efficiency actually. So the scaling actually is carbon sulfate. This is actually present in urine. So it's something you can't avoid. It will always enter the system. And this will condensate, or what you call this, precipitate on parts of the system, and you see this kind of brown scaling which will happen in parts of the system, and which can actually block your system, and for this you will need to do maintenance. Now, what they're trying to do now on the current system is to lower the pH to try to prevent this, but actually the solvability of the carbon sulfates is kind of independent of the pH, and so it will always precipitate somewhere in the system. So how to avoid this? Well, is to get the carbon sulfate out of the system, actually, and that's what we proposed and which we did. And the second problem is the formation of biofilms, which you also see on systems on Earth, because you have the organic components in your system. You have, by definition, a biological system, and these bacteria will tend to grow in such a system. Now, again, you see here actually an uncontrolled growth of these bacteria and biofilms. So how to improve this is actually by controlling this biological growth, because you can't avoid it at the end. So that's the system we built, and which is actually similar to the system which is on the space station, but with some important improvements. So this part here, this crystallizer, actually prevents scaling in the system. And why it prevents the scaling? Because it removes the calcium directly after the urine is collected. You will not have the scaling actually later on. The second part is this bioreactor, actually. And this bioreactor, so are bacteria, and they will decompose the organic components. And so there will be some bacterial growth there, but only there in this bioreactor, and not the uncontrolled growth further on in the system. So actually by doing this, you have solved both issues. We've been running this system, okay, it was on ground, during 3 months with an efficiency of 96%. So what does this mean? If you go from 75% to 95%, it means that you save about 6 tons of water that you don't have to take up to the space station. Or you can do the calculations. I think I saw 25,000 per kilogram. That would add up at $150 million per year that you could save by improving the efficiency of the system. Sorry. The same system, we actually have implemented this on Antarctic, and the only difference actually is that it also uses the black water from the toilet flush. This is also working very efficiently. It's also working autonomously. It's monitored from within Belgium. So it's the Belgium Antarctic Station. And it achieves a water recycling of 96% over the last year. To start up, we use water from snow. So you could ask why not always use the snow. Well, actually, the recycling uses 80% less energy than melting snow water. So it's actually more energy efficient. And that's one of the things that you have to take into account here. You're limited in energy. This is a fully sustaining, self-sustaining Antarctic station. So we don't use fuel and so on. So we use wind energy. So therefore, it is limited, the energy that we have available. Okay, so this is another new technology that we are developing with bioreactors. It's actually to produce hydrogen. You can use it on Earth or in space, and you're actually using bacteria and contaminants to produce hydrogen, which is more efficient than using oxygen and external energy. And last is some very recent development that we are doing. Oh, there was, okay. Some recent technology in the frame of in situ resorts. And there the challenge is that, yes, you can extract water from rocks. Yes, there is ice on the moon that you could extract. But this water doesn't come in a form that is immediately usable, so you will have to condition the water. This is exactly what we are looking at, for instance, with this technology as membrane distillation modules to condition the water so that it can be used, for instance, for drinking water or for processing kind of technologies. So the main message that I want to convey here is actually on this last slide, is that, well, in the life support technologies that have been used up to now have been very conventional. And so we've been looking really in the techniques from water treatment and so on, where you actually have to look what is the source of the water, what is the use of the water that you want to use it for. Is it drinking? Is it processing? Is it to wash yourself, or is it for something different? And then to define exactly which type of technologies, and there are all kinds of technologies. There are physical-chemical technologies, there are biological technologies that you could use. And mostly, let's say the answer is the correct combination of some of these technologies will deliver your most efficient system, and that will improve our life support systems in the future, and will hopefully then make life possible in space. Thank you.
Right on time. Yeah, I got it.
Yeah, sorry. That was
Yeah,
yours.
sure. Thank you, Frank. And I maybe I shouldn't say this, but one of the most interesting points that I learned about was on Antarctica. I mean, it's a remarkable, and even with the use of wind power, I guess one day what we learn in Antarctica will be good in outer space. It's my pleasure now to introduce our next keynote speaker, Klaus Slenska, Business Unit Head at OHB in Bremen, Germany. Klaus?
Thank you, Jeffrey, for the introduction. And thank you, Frank, for the good overview from your presentation about the hardware. Thank you, Asgardia, to inviting me to be here. And thank you to the audience listening to the presentation. My name is Klaus Lensker. Just a few words to my background. I'm neurobiologist, so not an space engineer, but working now since more than 30 years in the space business, 25 years now at OHB System in Bremen, which is one of the large system integrators in Europe. And I'm heading the life sciences department there. And what you see in parallel here, Blue Horizon, that's what we started 3 years ago. We opened a company in Luxembourg, the Blue Horizon Saal, and 9 months ago we opened a second Blue Horizon company in Germany, where we will transfer all our life sciences activities based on the fact that our owner of OHB, Marco Fuchs, is very enthusiastic, let's say, that life sciences will be the future also for space exploration, and all the, let's say, the word bio will become more and more important. And we are focusing not only on institutional money, yes, we do, partly, but we want to create technologies, or we have our business plans established like this, to have technologies which are ready for, or which has to be developed for space exploration, but they have to be clearly applicable to Earth. As I'm a biologist, and I'm happy that Frank showed Mark Watney out of the movie The Martian. You know, Mark Watney was also a biologist. So he was able to survive on Mars because he used biological methods and some physicochemical methods to get from the hydrogen to the water, what he needed for the potatoes and so on. In my presentation, I will focus here not too much on hardware. I want to first tell you a little bit about what is life support at all, what we have to consider. Life support systems in general. Why do we need them? Life support systems are necessary to preserve the biological autonomy of living organisms. And that's independent if you talk about a human or an animal or whatever. Because they are isolated from their typical biosphere. So already a scuba diver with the compressed air bottle uses a life support system. That's the compressed air bottle, because he is out of his normal environment. He's in a not applicable environment for his normal tasks. A controlled physiological and psychological acceptable environment is the basis. We know from the space history that in the first, let's say, space stations, they were not designed to be very psychologically compatible. So people were very unhappy. So life support also need to take this into consideration. To give you an overview of what life support is, we are talking about non-regenerative ones versus regenerative systems. So life support is not easy, let's say. It's a very complex topic. Open loop systems, closed loop systems. We heard from Frank about physicochemical systems and the hybrid systems. And finally, we end up in the fully bioregenerative systems. Non-regenerative systems, you have no recycling possibility. That's like scuba diving. You have your oxygen, and then it's gone. Yeah, but you cannot recycle. A regenerative system already includes resources, what you want to recycle, oxygen, water, food potentials, but it's very weak defined. And then we come to the open loop system. We have seen on the space station life support system, there are a lot of open loops. CO2 is vented. Hydrogen is vented. One of the most energy efficient molecules we have, or the most energy efficient molecule on Earth, we are venting it. Because we are afraid to use it or whatever, we could use it very efficiently. And we have to use it in the future. We have big advantages. They're simple, highly reliable, standard use. But we, as we heard already, we need resources continuously. and with increasing mission duration, and we are here talking about Asgardia, we are going as a nation to space or to outer space, we are going to moon or where else, and with increasing crew size, that will not work. So we have to close the loops. So we have initial resources from Earth. We have to have, as we heard before, we have to take water and then we have to recycle it, hopefully to 100%. And we have non-useful waste products are processed to recover useful resources. And we have disadvantages yet. That's the higher initial system mass. We have no high technology maturity at the moment. And the Earth is increased thermal and power management. So then we come to the final goal. What I want to talk about, what is a bioregenerative life support system or a closed environmental ecological life support system? And there the key word is appearing the first time, it's ecology. And ecology is one of the basic issues we have to think when we want to go for longer stays outside our Earth. We have living organisms in the system, plants, bacteria, animals, so a whole system. We have to potentially able to provide food. We need basic research, and I will come to this point much more in the next slides. We have a large volume, intensive maintenance, high power requirements. However, we can provide Earth-like environment to the crew, and we have to have the research we're doing is highly beneficial for our Earth's understanding. Where we are today. When I look into my history, I already in 1996, I bought the book from Peter Eckert, here, Life Support and Biospherics. We have another standard, which is very good. It's from the NASA Earth to Lunar Cells Evolution. These are standard books when you're working life support. When I read today Peter Eckert's book from 1996, I'm really frustrated because I do see really not a large development we have achieved to come to really fully regenerative life support system. We have done a lot of technology development, yes, but we have not reached to understand bioregenerative life support. Our life started 3.5 billion years ago, first life. Before we had a gap of maybe 1 billion of year, and there before Earth was, let's say, full of volcanoes, no life occurred. That was the time when the moon was bombarded out of the Earth. So the moon reflects Earth status 4.8 billion years ago. So life comes later. We all underlying Darwin's law. That's clear. We have a clear evolutionary process. We are living in the so-called biosphere, and with industry, we started to create a technosphere. So we have now two spheres working together, and we changed, in the meantime, the biological balance in these systems. And you see that it's a nice picture with the ice bear in the ocean. And I would have shown you this picture already a year ago. I do not need Greta Thunberg to talk about climate change. We know all about it. And we are aware, and especially the people working in bioregenerative life support know it. Yeah? So when we have this vision to go in a big, let's say, station, rotating system, what we have, where is artificial gravity, or we go to a fully functional Mars or moon base, or we're talking about settlement, what it's a lot of people talking about, we have to avoid doing the same mistakes what we have done here in our biosphere 1, because we are creating a new biosphere somewhere outside. So we have to understand all these processes. And there, the challenge will be to keep the biological balance, what we destroyed here on Earth, and we want to come back to that, also in such a huge life support system outside Earth. I can 100% say that this picture will fail. Yeah, when you will really will be done like this. You see the many houses here and the few green plants that will not work because the CO2, what we blow into the atmosphere when building these houses is so high, then we need the same equivalent mass from the production of the CO2 for the houses in creating biomass. So to keep in the balance, to keep in the equivalence. Potential solutions, what we have done in the last centuries. Some examples. We have nice, big, let's say, research facilities. The one in Shenzhen, China, very new. I visited 2 years ago. We have the Lunar Palace. We have in China 3 of these huge, let's say, closed systems where people can live in it, where we have hydroponics and there's lettuce grow and. We have in Japan the sieve, which is a very bit quiet in the last 10 years, what the world is doing there. One of the most famous systems is in Krasnoyarsk, Siberia, the biosystem, where fundamental work was done long time before we in the Western world talked about life support systems. So I think Krasnoyarsk is a major player in that system. As you know, the Biosphere Tour a few years in Arizona was completely in the press, and it was mentioned that it was a failure. It was not a failure at all. The scientists said, playing God and setting up this Earth-like system, it has to be a closure of 100% maximum. The engineers did the best and closed the system to 99%. What happens? Right from the beginning, the oxygen production was too low, or let's say the oxygen consumption was too high. There was a mismatch in the calculations. If the closure degree would have been 96%, we would not have seen this effect. So it was a big success, even it fails, yeah, in the overall system. But it's very huge and it's very complex, and today the related universities cut it down in single pieces. Biospheres in space, I show one piece of hardware. I think it's the only multi-species system ever been in space. When we do not say the space station is a multi-species system, because indeed it is. Yeah? There are not only humans. There's a lot of biofilms, there's a lot of bioburden, there's a lot of things. Yeah? But in this piece of hardware, we had created a small ecosystem from fish, water snails, plants, bacteria, and so on. And we had it 3 times in space. Unfortunately, we lost it on STS-107. But the data we got showed that from the ecophysiological aspect, we observed no changes after 16 days in space. We observed a lot of different changes with the animals. The newly hatched snails inside were independent from gravity when they came back. They didn't do the same as their siblings doing on Earth, crawling down and hiding. They were, okay, I have the 3-dimensional space. The fish were very interesting because after 16 days, the biological cell system already reacted. For what do I need a swimming bladder in weightlessness? Rejected. So they did this. They could not swim anymore when they came back to Earth. They were laying on ground. So I can hypothesize would it be in the 2nd, 3rd, 4th go. And we started together with the national agency in let's say, thinking in a different way. The first way was, okay, is it really necessary to put for a life support system the human in the middle, yes or no? Or can we think different? And we started to say, okay, at the beginning you have a small house, then you have 2 houses, and we combine the houses. And let's say one house is producing, is heating, has a heating system, so we have to combine the heating system. So, and it's growing system. So it's a little bit shown here. You have systems are not working, and then you start with one working system, and you identify what is ongoing there. Then you take the next one, and so you increase, let's say, your knowledge, your scientific background from one system to another. And that's what was also shown. That's from the German Space Agency, DLR, developed in that pyramid, which is more or less still valid, but with changes. But that was in 2009. Risk reduction was at one point for redundancy had to be implemented and. So, but how to come to the next step? So we invited scientists and asked them, shall we do? What is the first step of these modules we created? And you see we presented them a lot of, let's say, aquatic systems, and so on. They said, please start with a photobioreactor model. That was the highest, let's say, value. They said, please start with this. And we did this. Yeah. Today we have a lot of photobioreactors. I do not want to go into detail what we are doing since more than 9 years now with the photobioreactor development. But I can tell you, I had to learn a lot. When I started it, I thought, okay, since 30 years we are talking about biofuels with green algae. There should be a lot of things available. But when I said, okay, we close the loops, we want to close it, we didn't find the scientific community for that, because the only thinking of the scientific community was you have a bioreactor, and the only thing is to create a lot of biomass, as much as possible, because biomass is the overall goal. And that's we have to change. So you see here a lot of pieces of hardware we had to develop up today to understand how to come to close a photobioreactor system. We have to develop, for example, here a cell separation and gas exchange unit. Cells has to be separated before you extract the oxygen out of the loop. We have to develop new photobioreactor system. We developed new lab-on-a-chip system for, let's say, to measure ions in the water. We developed biofilm measurements systems. And you heard biofilm already from Frank before. Biofilm for us is a national issue. It has to be there. We are not running our photobioreactors in a sterile condition or in an arsenic culture. That's not ecological. Yeah? We run it with the contaminants of bacteria, of fungi, all as you would see it outside. When you go outside and look at a tree here, you will find the green algae, which are being in the photobioreactor around the trees. And there is not a sterile environment at all. So today, we know this first model very exact, this module. Now we have to open it again, the loop, and to identify how we can attach the next module. What we do with the little biomass we're producing, what we do with the oxygen. And we heard oxygen production for humans. Please be aware. A bioreactor on the space station for one crew member must be 5 to 8 square meters large, 2 centimeters thick, and the green stuff in it must be very dark green, and you have illumination like in Sahara. And then you will create enough oxygen for one human. So it's something for a base somewhere else, or for large stations, but photosynthesis have to be very seriously before telling a story about it. That's our story from Blue Horizon. We are not just going for photobioreactors. We are going to identify all the, let's say, loop closures, what we need. And you see, for example, why we are also in Luxembourg from the Space Resources Initiative. We need some basic components, maybe from asteroids or whatever. So coming from a small photobioreactor, maybe to a flight hardware system, where research on the algae can be done, to a large-scale system on somewhere else on the body. Also working with, for example, moon dust here to have higher plants growing on it. A lot of people ask, what is the commercial activity for, let's say, green algae? There are a lot of things. And how we can apply this for space, let's say, space colonies, or let's say long-term space, stays in space. We do not think the way of biofuels is the right way for out of algae. Cosmetics, let's say yes, because every human in a base will need it. Pharmaceuticals, yes, that's the big challenge, to have a space pharmacy developed on a very simple ways. Food, no. With algae, no. Already Gittleson from the Biosystem published what will happen when you digest your algae out of a photobioreactor. It's not very healthy. Fertilizers, yes, you can do out of that. Animal food, yes. And one point is, it's bioplastics. Bioplastics are very interesting. To bring algae in a plastic format. In bioplastics, we developed a new method. We are creating out of the algae surgical tools. Yeah? They are completely sterile when they are produced. You can break them down and you can recycle them. So recycling is the thing we want to have. Summary perspectives. If we want to leave Earth, so it's my really basic understanding, for longer stays we need bioregenerative ecological life support system. We need a better and complete understanding of our ecological biosphere. We do not need, let's say, radical environmentalists to do this, but we need to bring together the environmentalists and the space engineers. I know how hard this is. In Bremen, going to the university and talking to these people, going on the street, they say, whoa, you're coming from space industry. You just want to take money, nothing more. So we have to overcome this. We have to talk to these people and to come to a common understanding what we are doing. And that also that our investments are not, that we have to have a return on investment to be successful, but that this return of investment is positive, what we are doing. So we have to speak with them much more. And we have to need more money in this system. So I hope that we have venture capital or whatever investment people we can find, because we have to speed up a bit. We cannot do the same as in the past 30 years. Huge facilities are good. It's a good marketing effect. But when I go to Shenzhen, it's perfect for marketing. It looks quite good, but when I ask, what is that facility? Oh, it's just cardboard. What is this facility? It's just cardboard. It's fake, yeah, let's say. So we need to develop it. We need to spend money into the system. Short-term views are good, however, do not increase public awareness. Public awareness is a key issue if we want to be successful. So we have to not just show the public or to tell them space is nice, because when you look in the last space missions, how the awareness was, and when you compared it with the Apollo missions, how the public awareness was in that years, we have to do a little bit more. And we see what other private, let's say, investors do. We have seen, for example, in your presentation, all the billionaires, and they have extreme public awareness, and there we have to come to. It's not science fiction anymore. And last, all the research and all the investment we do for bioregenerative life support are very good, because they guarantee a better and healthier life also here on Earth. And by this, I thank you for your attention. Thanks. Later.
In Switzerland, doing a presentation on demonstration SSTO cost-efficient access to space.
Good afternoon, everyone. Well, I don't see the slide,
The white one?
the presentation. So, should I,
Take the white, yeah.
this one?
No, the big one.
The
Yeah.
big one?
Yeah.
Oh, okay.
And point to this direction.
Right.
And hope.
Good afternoon, everyone. First of all, I would like to thank the organizing committee, namely Ms. Dasha Surikova and Professor Floris Jutz, for accommodating my talk into the Congress program on the very short notice. In the 1960s, 70s, there was quite a bit of enthusiasm in the world as to the bright, imminent future of human advances in space and colonization of solar system. There was a popular song back then in Soviet Union, often transmitted on radio, about the apple trees blossoming on Mars. Today, half a century later, there are still no blossoming apple trees where they should be, on Mars. Well, the achievements are always measured against expectations. After the spectacular Apollo moon landing expeditions, public expected a lot of advancement in space, but nothing of a similar magnitude happened ever since. This does mean there was no progress or no important successes in space exploration and science after 1972. There were, of course, and quite many. It just means that the public expectations of that time were not met, and that's all what it means. However, the space expectations of the 1960s, 70s had firmly imprinted themselves into the public memory, and they won't go away. They continue to motivate the modern space aspirations, and Asgardia itself epitomizes this fact. Conquering the outer space is very much about logistics, which inevitably starts here on Earth. The logistics which is capable of breaking through the Earth's gravity in some technologically sound and economically viable fashion to begin with. The fundamental problem of accessing space was never solved to satisfaction when it comes to safety and cost. Chemical propulsion is used to access space for more than 60 years. Yet, the launch failures globally on average continue to be at the level of 5 to 10%, making insuring costs a significant part of the launch expenses. Due to the unfortunate combination of the inherently modest specific impulse below 500 seconds and small payload fraction below 5%, the chemical propulsion launch cannot be but very expensive to vast majority of the prospective space applications, particularly those which require launching small payloads dedicatedly. The current launch systems have the specific cost of launched LEO above $10,000 per kilogram on average, and much higher for dedicated launch of the very small payloads. It was understood a long time ago that the high cost of accessing space is the main obstacle for advances in space. In 1994, the major aerospace companies of that time, Boeing, General Dynamics, Lockheed Martin, Marietta, McDonnell Douglas, Rockwell, jointly sponsored the commercial space transportation study under the auspices of NASA's Langley Research Center. The results of this prominent collaborative research had shown that the launch to LEO market elasticity can start establishing itself at the payload-specific cost in LEO of 2,200 inflation-adjusted US dollars per kilogram, which is a threshold for second-generation launch systems. At a specific cost of less than 300 US dollars per kilogram in LEO, inflation-adjusted, a sufficient return on investment and profitable commercial launch architectures become possible. This is a threshold for third-generation launch systems, which also serves a criterion of the free market space economy comfort zone begins. The chemical rocket propulsion, being the first-generation launch system, will continue to serve humankind for a long time. But it is a dead-end path with regards to the low-cost access to space. According to the study, only the third-generation launch systems, which has much lower specific cost of accessing space, will allow significant expansion of human activities in orbital space. Within the area of possible technical alternatives to chemical rocket propulsion, in the context of launching payloads to LEO, the laser ablation propulsion stands out as the most meaningful, both technologically and economically. Laser ablation propulsion, being a thermal quasi-neutral plasma propulsion, demonstrates specific impulse over 7,500 seconds, while the payload fraction is to be over 30%. The prominent laser ablation propulsion experts agree that $300 per kilogram is a plausible estimation for the laser ablation propulsion launch to LEO specific cost, which makes the prospective laser ablation propulsion launch system, Laplace, a third-generation launch system. On one hand, Laplace can provide the low-cost technological solution to the dedicated on-demand launch to LEO of the pico nano microsatellites. More importantly, Laplace is positioned to enable the ground-to-orbit logistic framework and thus to trigger the advent of the free market space economy. It is feasible in every respect to develop and build within a few years the first industrial prototype of Laplace with its overall development and construction price tag on the order of building a single large telecom satellite. The overall time to raise Laplace to TRL-9 may take up to 5 years if the adequate financing is present. This slide is simply to remind you that the overcoming the Earth's gravity matters a lot. It takes delta V from 9.3 to 10 kilometers per second to go from the ground to LEO and stay there, which is almost 3 times more than what is needed to go from LEO to Mars. It is even more than what is needed to leave from LEO the solar system altogether. Indeed, getting to orbit is halfway to anywhere. Thus, in terms of logistics, separating the ground to LEO leg from any and all further space destinations has no sensible alternative. To address the issue properly, the ground to orbit logistic framework, GOLF, was proposed. Separating the ground-to-orbit flight from the in-space flight by means of the ground-to-orbit logistic framework, GOLF, with Laplace addressing the critical ground-to-LEO segment, can make cargo exchange between Earth and orbit so cheap and mundane that it will prompt to life the broad and diverse free market orbital economy, which will dwarf the currently existing market of data transmitting and collecting orbital services. GOLF will result in a new economical situation. The global market economy activities will expand in a full-fledged manner to the new geographical frontier, the low Earth orbits, which will create a set of technological and economical conditions favorable for the orderly expansion of humankind into the deeper space. As to making the solar system home, realization of Laplace will resolve, by and large, the bottleneck problem of accessing space safely, cheaply, dedicatedly, and on demand. Laplace in operation will help to bring the emerging pico nano microsatellites markets into the mainstream, and more importantly, enable the ground-to-orbit logistics framework, GOLF. Having GOLF in place and smoothly operating will lead to the era of industrialization and colonization of the Earth's orbital space on the free market principles. Then, the right conditions for development of the solar system logistics services, the backbone for the solar system colonizations, eventually will arrive. Summarizing what I've said earlier, first and foremost, there is no way to enable broad industrialization in space, orbital and deep, let alone its colonization, using solely the current access to space technology based on chemical propulsion. While the chemical rocket propulsion, being the first generation launch system, will continue to serve humankind for a long time to come, it is nevertheless a dead-end path with regards to the low-cost access to space. Secondly, and luckily, there is a practical way of accessing space which can fully validate the high expectations of the 1960s, 70s, and that is Laplace, which meets the third generation launch system criteria, being also safe, there is nothing to explode, dedicated and on demand. With Laplace fully developed, the industrialization and colonizations of orbital space on the free market economy principles can become a reality. Finally, it often happens with the new technologies that they are much cheaper to develop and to run than their predecessors. So the Laplace, which is to be immeasurably cheaper in development and operation than chemical rocket propulsion systems, to the degree that no public money may be needed at all to have Laplace fully developed and operational. Those of you who are interested to get deeper into the subject matter, please read my recent articles, freely available online. The QR codes of the papers are shown on the screen, and also in printed form available up there on the table. My time is up. Thank you very much for your kind attention, ladies and gentlemen.
Thank you. Thank you, Yuri, and you're obviously correct. I mean, one can envision an Asgardia at present cost of space transportation, and we all know that the price has indeed has to come down. And I hope, Yuri, you get a chance to talk with some of the sources of capital that are here who are looking for new ideas, and this is one where we certainly need to go. Okay, I finally know the background of the next speaker because it's myself, so I can, it's the first time I can introduce a speaker, but it's, and I'm going to time myself as well, so, but we're on schedule. But it's a delight for me to have a moment to talk about NanoRacks. I'm Jeff Manber, the CEO of NanoRacks, and I'll see it now. It's my turn to pray to the space gods that this thing. What did you find, Frank? Is it over here or over here? Oh, it's the white. Oh, that's why. Okay. Ah, okay. Look at that. So NanoRacks is, hard to believe, 10 years old. When we started out, we were the first company in the world to own and market our own hardware on the International Space Station. And in the beginning, there was a lot of philosophical problems. People at the Space Agency, the NASA, could not understand that a private company would want to own research hardware on the space station and market to whom we wish and set our own prices. And we've come a long way, but we still have a long way to go. And just quickly, we've really grown without investors. We've grown by increasingly having more complex hardware. I like to say that at NanoRacks, we're not in the hardware business, but then I show this slide. And we're in the hardware business where we can find something in the marketplace. And we started with little nano labs. And it was the first time you had standardized small 10 centimeter by 10 centimeter by 10 centimeter little labs. And I made a decision then, 10 years ago, not to patent it. And I wanted to have an ecosystem. And today, NanoRacks has competition with Ice Cubes and Space Tango. And that's what we wanted. We want to see the market develop. And so as much as possible, we try not to patent because we always believe we'll be better at getting the customers and building the market. And today, I don't have time to talk about it this afternoon, but right now, our biggest project is the commercial airlock, Bishop. It's manifest to go up next year on SpaceX in August. It will be 5 times bigger than the airlock on the space station, the Japanese JAXA airlock. And somehow, by some miracle, it's self-funded by NanoRacks. We've had some support from Boeing Aerospace and Thales Alenia, but by and by, it's self-funded, and we've already had it pay for itself in contracts. And we'll be announcing those soon. So we've really developed an expertise on the government space station, the International Space Station, on how to build cost-efficient hardware for the customer. And we have customers. We have customers in over 32 countries. They range from high schools and universities all the way up to, we count ESA and NASA as customers. And this is a big debate in Washington. In Washington, I show this slide, and I say I have NASA as a customer, I have ESA as a customer, and they go, "You're a hypocrite. You know, you're supposed to be commercial, and you have the governments as customers." Well, it's my hardware. I paid for it. I self-funded it. And if I get NASA as a customer, and if I get ESA as a customer, and if I get DLR as a customer, and it's after I've created the hardware and it's on my terms and conditions, that's commercial. But no, I mean, we just, you know, and if an ESA official, if, you know, Frank flew here, he flew on a commercial airline, and to Lufthansa, that's commercial, even though Frank's with ESA. I mean, so it's in Washington, we lose that perspective of you can have government as commercial customers, and we've been fortunate. We also very, very excited that the UAE astronaut who just returned, NanoRacks did the educational payloads for it, and we've just opened an office in the UAE. So, okay, but the reason why I'm here today is to talk about how close we are to populating the solar system with commercial laboratories. And usually in my presentation, I talk about all the things you can do in space, but that's what all of you have been talking about. So I elected not to do that today. Instead, I'm going to talk about the infrastructure and what we are doing at NanoRacks today to create the stepping stones in LEO, GEO, and in deep space. And so, but before I do, I'll say, you know, you've been talking, Klaus and Frank were talking about life support systems. We're beginning to focus on doing our own in-space research, and we're looking at microbes and bacteria and using the harsh environment of space to, as Klaus said, to help the environment, to help us on the Earth, as well as as we move on to the Moon and Mars. And I love this quote. This quote on the bottom here is more of a surprise to people in the United States, because in the United States we kind of know the Europeans are doing things in space, but we refuse to really acknowledge that the Chinese have a space program, and it's not just for political purposes. And they're actually doing some very, very interesting research in space and microgravity, the use of the microgravity environment. So I like to include this quote, mostly for the American audience, just for them to know what the Chinese are doing. So there's a new era now in the States. We are very fortunate that in the 10 years since I co-founded NanoRacks, we've been able to convince NASA and the other US government agencies to behave more like a customer. And I know that ESA is looking to do the same. And today we can send you to the space station for a fee that we now pay NASA, and NanoRacks has submitted the first few payloads on behalf of companies that will be doing commercial work on the station. And the other thing, which is really exciting, because it's there is, of course, I want to use space for research, and I want to use it for education. But you know what? It's a really cool place. And how do you get the public excited? And so you allow media, and you allow branding, and you allow other things to take place. And it's been very, very difficult to convince NASA to do this. Several years ago, we did an Ardbeg whiskey project on the station. And I can take an hour, and don't worry, I won't, explaining how we got that through NASA. And the other announcement by NASA at the time is that they're going to have commercial space platforms. And so over the next few years, we will begin to see one module attached to the space station, commercially owned and operated by a private company, and one free flyer. But we're not waiting for the NASA announcement, but we're beginning today on paving the road to living in space. And then, as my colleague said on the panel, we still know very little about what's happening in space. And this slide, I guess, is left over from when I talk a lot about science. So the idea, what we're doing at NanoRacks is an old idea. We've been working the last few years on repurposing the upper stages of launch vehicles and use them for commercial habitats, laboratories, fuel depots, instead of throwing them away. The diagram you see here is from Wernher von Braun, and this is when he was head of NASA Marshall. It must have been about 1960, and he wanted America's first space station to be the repurposed upper stage of a Saturn V. Well, our first space station in the United States, called Skylab, was the second stage of a Saturn V, but Wernher von Braun lost the argument. Johnson Space Center said, no, we can't repurpose an upper stage for, once it's in space. So the second stage that became Skylab was modified on the ground. What we're talking about doing at NanoRacks today is modifying the second stages once they're in space. And we've already made the first steps. And so we got funding from NASA, and here this was not commercial. Here, NanoRacks was a typical godless contractor, but we got funding from NASA to do a 5-month study to see if we could prove to NASA if you could repurpose an upper stage in space. And we worked with friends at ULA, and it took 5 months, and we showed, to the surprise of everybody, maybe including ourselves, that not only could you repurpose the spent fuel tank of an Atlas V once it's in space, but here's the cool part: you can do it without astronauts. I mean, that really opens the door to true exploration at a far less cost. And our partner in it, in the project, was Maxar, MDA, if you know them, the robotics people. And the robots that we're using are today on the surface of Mars. And I switched into the present tense in saying that we are using, because I can't say too much yet, but in the next few weeks we'll be announcing our first in-space demo. It's going to be launched in 2021. It will not last for too long. It will be just several hours, but it will be the spent upper stage of a launch vehicle, and we'll be doing some robot testing, welding, robotically. We'll be sending some biologicals. We're asking and we're working to see if we can spin it so that it becomes artificial gravity. And this is really, for us and for the community, a really good beginning to show that, number one, you can be innovative. Number two, you can be efficient. And you know what? You don't always have to, when we talk about the next generation of space stations, we don't have to be talking about manufacturing them all on the ground. But wait, as we say, there's more. NASA has put out a request for a proposal, and we plan to work with NASA on owning and operating the Free Flyer. What's really cool about the proposal, it's come out in draft form at this point, is that it acknowledges the Free Flyer will not be part of the International Space Station, that the owner and operator has to file with the United Nations. And I found that interesting. I can debate. I may want it to be part of the ISS because there's something called IGA, Intergovernmental Agency Agreement. But then part of me is kind of excited. My history, in 2000, was head of a company called Mir Corp, and we sought to lease the Russian space station Mir, and we had to work very hard with the United Nations, and we were located in Holland, and the Dutch government could not have been nicer in cooperation. And suddenly, in their midst, in an office in Amsterdam, we had taken control of the Russian space station Mir. And so there's only in space, only in the space business. And so I think we're coming up to a new era now where NASA is going to be promoting that they are a customer, one of many. And we're working now to develop a team of companies, organizations, governments who would make use of the Free Flyer. I want to say one more thing. Oops, you can't go backwards. Maybe you can. Nope, maybe you can. So I'll say one more thing we're working on in NanoRacks, and this was all scrubbed very carefully, and there are things I can't talk too much about, but we also have now picked up funding for a multi-year effort to work on repurposing of upper stages of launch vehicles. And that will be ULA, Atlas, it could be SpaceX. I'm in some preliminary talks with European companies. But now with this funding, and that will be announced in maybe a month or two. We're now in the business at NanoRacks on repurposing upper stages. And what's exciting for me is that, and Asgardia, and for all of us trying to do these things, is with this infrastructure, you can do a number of things. But in philosophy, number one, we'll be part of this whole new network of looking down at the Earth for commercial data and big data. We think it will be quite disruptive because as you look 5, 6, 7 years out, you're not going to be sending mostly satellites up from the Earth. You're just not going to do that. Most of them are going to be manufactured 90% on outposts like this, and the software uploaded, and you get deployment on demand, which is right now we're all striving for launch on demand, and the key goal we think at NanoRacks will achieve in the next 5, 6, 7 years is deployment on demand because you manufacture it in space. And they can replenish constellations and can do a lot of things that it doesn't matter about the weather, doesn't matter what's happening on the Earth. You use the launch vehicles to send up raw materials rather than finished. Second, we see them as in space laboratories to overcome climate change and working in ag tech and life sciences and microgravity. That's why we're so excited not to be attached to the space station, because we've all learned that when the astronaut's on the bicycle, it screws up the research. We just all learned that. And no offense to the astronauts, but we know that's true. And then also for an Asgardia, this is the building blocks. It's not the final solution, probably, but it is the building blocks to have the fuel depots and logistics centers. And if we can provide them using the upper stages, that's the expertise we want to develop. So that's where we're going at NanoRacks, and thank you for your time. Okay. And I think now we're going to have a brief what do you call it, panel, roundtable. And I guess do you want me to, I'll moderate it. I'm up here. I'll do it, okay. I took notes, so let me get my book.
I'm Fleur Swartz.
Oh, okay.
I want to make an announcement regarding the picture which we will have to take.
Okay.
Just after the session.
Okay, so just come, where are you sitting, right? Okay. I think there's three of us. I think there's three. So, okay. Okay, join. Okay. Okay. So I had said earlier this morning that I wasn't sure if I would moderate because I know very little about the topics here. But maybe that's true of many moderators. I don't know. So, but I learned a lot by listening to my colleagues. I guess I'll start on the question of life support. When we look back, it's very politically correct to say in the United States today, we're going to return to the moon, this time to stay. And we regard it as a mistake of our politicians that when we went to the moon the first time, we didn't stay long. Listening to the two of you, I had the thought, and correct me, I know very little about this, that you know what? We couldn't have stayed on the moon for a long time in the 1960s, 70s. I mean, we always say it's like, oh, if only we had the willpower. But listening to you, we could not have had a colony on the moon. I'm not sure we could have one today. And if you could just address the other thing from the States, I brought not only my suitcase, but a perspective from the United States. The other thing in the States is, oh, we're going to return to the moon by 2024, this time to stay. So my question is, can we return to the moon this time to stay? Is that technically feasible? If not, what does it take to do that?
Yeah, well, I think that's, it's not technical and feasible it's more a financial perspective because obviously the
But could we have done it 25 years ago?
well, the alternative is obviously to bring everything from ground.
I see.
But that's financially probably not sustainable.
I see.
I'm not so familiar with the Apollo program, but I understand it has been a huge financial endeavor, which was probably not sustainable in the longer term.
Right.
So, in that respect, I would agree. US could probably not have sustained a longer presence on the moon in the early 70s.
So,
I would say, when you going back to the Apollo era, there already were identified a lot of risks. For example, Apollo 17, when they would stay 5 days longer on the moon, we would have a solar flare, and most probably they will not have had a chance to return. So there's the first fact is shielding had to be developed, and we at the moment we do not know exactly what is the biological dose, for example, from the cosmic radiation. We have at ESA a topical team on this issue. We do a lot of, let's say, research in that field. But as I said, there are a lot of open questions still today. From the life support, I would agree with you. You know that if we can bring, if we have, it's a financial problem. I guess actually 1 kilogram is 1 million euros or dollar.
to the moon, yeah.
Yeah, to the moon. So you can, if you have enough money, it's possible. So, but if you want to stay really a long time on it, you have also think on the risk you have to give to the crews. When you look at the picture, Cernan, Schmidt, the moon dust, it's a tremendous issue, and either you isolate the crew completely from the outside, or you take the risk that they inhalate the moon dust again, and then it's similar, quite similar to asbestos. So we have to realize a lot of issues have to be solved before returning and living there.
Before I ask you a question on propulsion, one more question here. Listening to both of your presentations, I was struck by how much I'm focused on, we call in the States the ECLS, life support systems. I was struck by how much you seem to be going down the road to have an organic ecosystem solution. That if we're going to have sustainability in space, we can't just keep bringing the hardware up. That we have to generate the oxygen, have organisms that do the recycling. Can you just talk about that a little bit? Are we at the beginning of a tipping point where we're going to be looking at organic solutions, or are we not even close to that yet? Can you talk about that sort of interface between the hardware and the ecosystem?
From my point of view, I think that's correct. We are at the beginning.
Okay.
At the beginning. So when you the issue of food, you start with fresh food, frozen food, canned food, and then the mission duration increases. What do you do then? So you have to have a food source. We look for when we take the movie Martian, how long he were able to survive with that technology he had available? A few months.
Mm-hmm.
After that, also there would be problems created. So the, let's say, organic way to go, it's a long-term goal, and it is for sure in parallel the physical-chemical system has to be combined at the beginning. But when Elon Musk speaks about settlement, then we need to have a fully functional, organic, ecological award system.
And we're a long way from that.
Yeah.
Okay, interesting. So you would put up the slide, right, that has the getting to space is halfway to anywhere. Was that Heinlein or?
Yeah,
it's Heinlein, Robert Heinlein. And so when you're looking at advances in rocket technology, launch vehicle technology, Are you focused on getting from the Earth to space, to Leo, or are you thinking also from Leo to anywhere?
Jeffrey, as I outlined, actually, it's going to Leo and also Heinlein
Yeah.
outlined
Yeah.
in his famous, actually, book. Going to Leo is critical. It's
Yeah.
the most critical part. And of course, humankind can try to go anywhere and doing different things anywhere, as it does, as a matter of fact.
Mm-hmm.
We're talking about also asteroids and everything.
Mm-hmm.
But it depends on willingness to mostly currently to spend money on science.
Mm-hmm.
We're not talking about actually colonizing anything at the moment.
Mhm.
And I believe before colonizing orbital space, it won't be possible.
There may be some people with capital, and there's some folks here who are in positions of authority. What kind of capital do you need to get going for your research? Here's your chance to.
Well, I mean, as I mentioned, it would basically to build a prototype
Mm-hmm.
first
Mm-hmm.
would take, I mean, to develop and build
Mm-hmm.
would take something on the order of the price of large telecom satellite.
Mm-hmm. Okay. Okay. So probably you need some sort, or in the beginning you would probably need combination of private and government capital, I would imagine.
I mean, I do not rule out, of course, government capital participating in this, but I believe that it can be done without it as well.
Okay. Yeah, there are some projects. Do you have a question? Is it? Oh, that's true. Yeah. Question. Forgot about a question.
I have a question regarding the life support systems and the doability. Let's say certain problems like in radiation, we kind of like know how to solve it because the science is already at that level that we know to protect. Okay, not all, we know not all details, but many. But is it good for life support systems to make it go and work? Is it just a question of capital and money, or do you think there are still really like essential questions of which we don't know the answer yet?
Answering that, I would say, yes, there are essential questions we have to answer. And I addressed it a little bit, but in my presentation when I said maybe we should not think about to put the human in the center of a life support system. Because that, if you do not do this, you open your view in science much wider, broader. Because then you are able to adapt your life support system to a potential new environment. And that's important. And that's also something we have to think about. When I take a green algae culture, decrease the environmental pressure, 50% are dying, but the remaining 50% have a higher oxygen production as the whole system before. So we have a cheaper system with less organic mass adapted to another environment. That's the same with radiation levels. We can adapt the life support and then put the human back. The life support system must not be Earth-like. And there are a lot of questions we have to address before. When someone says go to the moon, there are special questions. Go to the Mars, there are another questions we have to solve.
Why are there other questions that have to be? What's the difference between sustainability of life on the moon and Mars?
For example, when you think about the resources you have to use on Moon, on Mars, there is, as far as we know today, I'm using, for example, 3 different simulants in the lab to grow higher plants on it. I was very lucky in 1996. I stayed at Steve Schwarzkopf's lab at Lockheed Martin, and we investigated Apollo 17 moon dust and higher plant growth on it. It was impossible at the time. Today it's possible. We're using the new Orbitech systems. We can demonstrate with a few methods, let's say, it's possible to grow higher plants on moon dust. It's a completely different story when you want to do this on Mars. On Mars, you have a lot of peroxides in the upper layer that will kill you, all the bacteria there. You have to dig a little bit into deepness, so you have a different composition. So it's changing your methodology. So that's why it is the in situ resources are different.
Interesting. So, is
on-orbit manufacturing. Do you see this fully automated, or do you see a role for humans there? Because if you look today at industry, terrestrial industry, one of the most automated industries probably is the automotive industry. But we still have a lot of qualified workers there in the automotive factories doing the final assemblies and things like that. So how do you see this? And I'm asking this from a personal question because I might want to have a job after my exec career.
So just, you know where to send any CVs. We today at NanoRacks are already in the business of deploying on demand as much as possible. So we've deployed over 250 CubeSats from the International Space Station. And when this, and we deployed the first satellites, Aspire and GomSpace, and we helped bring about this wonderful time that we're in. But one of the things that we have found is there will always be a niche for the space station, and in this case, the human-rated space station, because we found satellites on the station for a month or 2 months, and then when they tell us to deploy, we deploy. One of the problems is we have coordination with JAXA and their airlock, and it's one of the reasons why we're going to have our own airlock, is a little more commercially run. We've found that along the way, we have found that humans add some wonderful value adds you can't do automated. We now have the astronauts review some of the fragile and large satellites, and they have encountered at times finding some problem before you push it out. We also have we had 1 or 2 satellites where the astronauts added on modules, and it was the first time you had something added to, and it made it very complex that could not have been really sent up. And so first answer to your question is, today we're already doing the sort of, we call it stash and deploy, have it stored in orbit and deployed, and the astronauts are a wonderful part of that. And so I think going to the future, there's always a role for that extra, for the foreseeable future, a couple of decades out, where the humans come in and they add something, they check something, and so I would see that role. I do see a tipping point where for a standard, let's say the planets of the future, the spires of the future where they're doing 200, 300, 400, they're going to have an automation line, I hope, on one of our free flyers. Maybe you send up the sensors, a little robot connects everything. We're very close to that today, so I see it being mixed. No. Yes, sir.
Well, I have a question for the two of you, Mr. Member and Mr. from Laplace, about the launching. Up to now, we are launching only completed systems. Mr. Member is suggesting that we could, in future, probably launch materials and produce in space with 3D printing or whatever. But it's a very cheap way of getting mass into orbit.
Well, to my knowledge, the cheapest way is laser, which is also electromagnetic, by the way.
Okay, there you go.
And I mean, it can be very cheap because it practically doesn't, the rocket, or we can say, I see it in future as basically a container link. It will be sort of container lines, you see. So these kind of things really do not carry much of fuel at all. So it will be always over 30% of ratio. The payload ratio. If I answered your question.
So I think he's being very polite, and what he really wanted to say was, please read my paper. So if you read the paper, you'll be able to.
Thank you, Jeffrey.
And basically, the journal publishes sometimes. There are interesting materials that provoke debates because they try to look beyond the known. So, some time ago, Kirill Pletner's journal published an article by a Russian professor at Leonov who was exploring the possibility of the quantum propulsion. And he was stating that this kind of propulsion would allow one to get to Mars in 42 hours. That provoked a huge debate in the Russian media. And so this is a question to Mr. Pigulewski, our speaker. How
I would
do
love
you
to
think-
answer, but, but actually I'm kind of talking about Earth to orbit.
right?
I'm not talking about further, right?
Oh.
So I believe I won't be in position to comment on this in a professional way. I'm sorry.
I see. Thank you so much.
Not at all.
I appreciate it.
Especially I didn't read these papers. So,
Yeah.
I mean,
I think it was 41 hours. No. I have, when I was...
I'll read it.
Yeah. When in your talk class, you were talking about, if I understood you correctly, you said one thing that was surprising to me. You said you don't want more public awareness.
No, I want more public
Ah,
awareness.
okay,
Yeah.
good. I thought it said,
And we have to have more public awareness.
Okay,
It's too
okay.
low at the moment,
okay,
and we have to go outside to say and clearly give the statements. And I know how the situation is, for example, in Germany, and I did my first experiment in 1993, and we were not allowed by political reasons to talk about it because we are flying vertebrates into space, you know. And you can, that's something what was critical seen, and my personal opinion is we have to talk about these experiments, and I think all the scientists will agree here. We have all our reasons, and there are good reasons to do the experiments, and we should be allowed to talk to the public.
Well, you raise a macro, you raise a bigger issue that maybe we can all just talk about for a moment. A lot of what we do in space exploration is, a lot of it is loved by the public, but there's a group of the public that dislikes what we do in space exploration for differing reasons. You mentioned animal research, that of course is frowned upon, or there are a lot of people who are against it. Richard Branson goes around the world saying he's for climate control, and then yet he owned a aviation, a plane company, and he has a space company, and people blame rockets for, being pollutants. We are here because of Asgardia. The whole concept of colonization, at least in the States, is a very negative thing to a large segment, not large, to a segment of the population. It has in America, it reminds us of what the Europeans did to the first people in North America. And so how do we, who are here because we believe in the concept of having a space nation, and doing research and living. And I'll add one more thing. Jeff Bezos has talked about having millions and millions of people in space. Musk, just remembering more, Musk has said he wants to transform Mars. There's a lot of reaction in America. How dare you transform Mars? You're just a bunch of billionaires. And we have to keep Mars clean. And so a lot of the goals that we have are disliked by a bunch of people. How, I address the panel, I'll address the audience, how do we show that whether it's the survival of the species, whether it's cleaning up the earth, as we heard, whether all sorts of reasons, how do we go from having a core group of people fearful of what our plans are for the solar system to embrace it? Is that? And if we can solve that, then we have lunch, okay? Then there's lunch. Yeah.
Hello. Maybe I have a question about this, a question about your question. And my question is, which might be an answer to your question. And this is, are your companies in any way trying to study or do some research on the possible impacts that, let's call it colonization, could have on external, maybe space, the moon or Mars? Because I think this is quite complicated and unpredictable because we don't know much yet about that. So probably the answer is we or you should do research about that and show that you are taking care of this aspect of space exploration, so things will be probably of low impact, and you're doing your best to do that. Maybe that might answer your question. But it's also a question for you.
Well, I think in general that's something which is done looking to the social, economical impact of space, and I think for some aspect of space, I think it's fairly easy to demonstrate it as you look to satellites and the benefits. I think Mark Buggett has been talking about all the data it brings and all the things that you could do with this data as weather forecasting and so on. I think for exploration, it's a bit more complicated, as I think the return probably lies in a further future. And so one of the things that we are looking at, and I think also Klaus mentioned, is that by doing these things, that we look also to the benefits on Earth. If you're looking in building closed loop systems, waste recycling and so on, you really have to understand these systems. At the moment, we have systems that work on Earth, but a better understanding could even improve the systems that we have on Earth. So there is some impact. Is this sufficient to convince all people? I don't know.
I agree. That's what you said. There is we have to be more. I saw it at the last month. We had that 50 years moon landing, and a lot of media came in my laboratory and they asked, "Oh, you have there a new project, with printing living tissues, skin and bones in your laboratory. We're developing such a printer for space exploration." And I said, "Yes, it's nice for space exploration. Maybe when you go to Mars, you need this, absolutely. But think about regenerative medicine. What is the really benefit for Earth when you do this? That's an investment goal to do this. When we, for example, when we start thinking what Elon Musk said, terraforming or whatever, forming the Martian atmosphere. Yeah, what is the behind? We study, let's say, cyanobacteria being more efficient in a CO2 atmosphere, a highly CO2 atmosphere, or we think for more halotrophic plants. That's really something what you can adapt to ecological system on Earth. So maybe we are not the best selling marketing people. We should maybe give it to professionals to do it.
Right.
Yeah.
Do we have time? Do we have time for more? You want to wrap? Okay, we're gonna wrap it. Thank you. Thank you, everybody. Thank you.
Thank you.
Thank you.
Okay, allow me to make two remarks.
So you did.
As you know, this is the first. This is the first Asgardia conference, and so I would like to ask you all to take part in a picture. So we will take a group picture at the stairs. Then we can all fit on the stairs, so it will be taken from below. And then after that, after the group picture, there is obviously the lunch. May I urge you to be back at 5 to 2, because we have a very important award ceremony, which is at 2 o'clock. So first now all go to the picture, the group picture, and then the lunch, and then be back here at 5 to 2. Thank you.